Tri-state buffer is a logic block that has three states, so it is called a tri-state. And the three states are basically, it can be in the 0, the output could be 0, the output could be 1, or the output could be Z or an high impedance state. So let's see, on the right hand side we can see that this is the symbol of a tri-state. The both of these are the symbols of a tri-state. So here we have just the enable bar as shown as the input. So the behavior of a tri-state is that if the enable is 0, we do not care what the input to this tri-state is. We just output a high impedance state, which is Z. So what it means is that basically we have no connection between the input and the output. So we have A here, the switch will be open. So this is the high impedance or Z state. But if the enable pin is 1, we just buffer this output. So which means that if the input is 0, we output 0. If the input is 1, we output 1. So if the enable is 1, the switch is closed, and we can see this as a switched closed, or basically a transmission gate. As we saw in the previous slides, transmission gates could act as a tri-state buffer. We have only 2 transistors. This is a good sign because we need very few number of transistors to build this kind of tri-state. But the problem of this transmission gate buffer tri-state is that it is non-restoring. So what do we mean by non-restoring? A non-restoring tri-state passes the noise on its input. So if we have a noisy input here in the A, our output will also be noisy. So this is our transmission gate tri-state, which is called a non-restoring tri-state. But we can build a restoring inverter or a tri-state inverter, so that produces restored outputs. So while building this, we can see that this will violate our conduction complement rule because we want a Z output. So this is how we should build this kind of tri-state inverter. We have 2 PMOS transistors connected in series and 2 NMOS transistors also connected in series. So one of each NMOS and PMOS will be connected as our input A. So enable bar is just the inverted output of the enable. Okay, so we have just one symbol, enable, signal enable, which activates our inverter, tri-state inverter, and our input A, which should be copied to the output invertedly. So when we have the enable pin set as 0, if enable is 0, this NMOS transistor will be off, and similarly if enable is 0, the inverted enable or enable bar will be 1, and similarly this PMOS transistor will be deactivated. So we have an open connection here and here. So our output is in a floating state. This floating state will be our Z output or a high impedance state. But if we have a 1 on the enable pin on the second slide, the second picture, if we have enable equal 1, then this transistor enable is 1, our NMOS transistor will be on and enable bar will be 0, and this PMOS transistor will also be 1, and hence these two transistors will be conducting and will create a switch which is closed. So we have just a CMOS inverter gate whose input is A and output is Y. So if enable is 1, our output Y will be A bar, but if enable is 0, our output Y will be high impedance state. So this is our symbol for the tri-state inverter. This is our A, this is our Y, and this is our enable pin. We can also write explicitly the enable pin, enable bar here, but both of these symbols are the same and represent the same. So both of these symbols are the symbol of a tri-state inverter.